Okay, let's get things started with chapter 2. And a lot of this will be redundant with your sophomore linear algebra experience. Some of the notation's a little bit new. I kind of like the way we did things in sophomore linear algebra a little bit better sometimes, but I'll adhere to the textbook's notation. Chapter 2, vectors and vector spaces. It's a theory of matrices class, but of course, vectors and vector spaces play a huge role. 2.1 is operations on vectors, and you know what you do to vectors. You add them together and you multiply them by scalars. You take linear combinations of them. So in this section, we'll define arithmetic operations on vectors, vector addition, scalar multiplication. We'll reintroduce a lot of the terminology from sophomore level linear algebra. Our notation, be very careful, the notation is a little bit different in this book. Okay, a real vector space is a set V of vectors along with an operation of addition, represented the obvious way, of vectors. We can add vectors together, and an operation of multiplication of a vector by a scalar, taking our scalars in here to be real numbers. And we require that this addition and scalar multiplication satisfy the following. Actually, this is a definition out of my sophomore level linear algebra notes. Notice, as we get things going, we're not putting any special notation on the vectors. They don't get little arrowheads like they probably did in sophomore linear algebra, maybe in a physics class. They're not bold-faced in this book, as they are in many sophomore level books. We're just using letters to indicate vectors, and we're just using letters to indicate scalars. Of course, the pattern, there's a little bit of a pattern. The vectors are letters later in the alphabet, and the scalars are vectors earlier in the alphabet. And they're going to say somewhere along the lines that, well, it's clear from the context whether we're talking about vectors or scalars. Yeah, maybe. I wish we had a little more sophisticated notation. But, you know, at a graduate level, this is not an uncommon notation. So you have to get a little adapted to thinking of every little letter that we put down as possibly a vector. Presumably, it's clear from the context. And we get 8 axioms, or 8 pieces to the definition of a vector space. The first 4, labeled A1 through A4, deal with addition. The second 4, labeled with S's, deal with scalar multiplication. And we require that the sum x plus y, x and y vectors, plus vector z equals x plus the sum of y and z, associativity of vector addition, x plus y equals y plus x for vectors, commutativity of vector addition. There exists a zero vector. How can you tell it's a vector? Well, because it's in the set V, the set of vectors, such that 0 plus x equals x. That is, there's an additive identity vector. And for any vector x, there's another vector will denote negative x, such that x plus negative x equals 0. How can you tell that's the zero vector? Because you're told upstairs x is a vector. So the equation wouldn't make sense unless we had vectors on both sides. Usual stuff, we've got an additive identity, we've got an additive inverse. Every vector has an additive inverse that produces that additive identity. When we go to scalar multiplication, we get a distribution. Scalar A times x plus y, x and y vectors, is ax plus ay, distribution of scalar multiplication over vector addition. To say distribution, you have to have 2 operations, one distributing over the other. Here we've got the scalar multiplication distributing over the vector addition. Here we've got scalar addition and scalar multiplication. A plus b, scalars, times vector x equals vector ax plus vector bx. Here we're distributing the scalar multiplication. I say we're distributing the scalar multiplication over the scalar addition, stated somewhat differently here though. but it's a distribution. We've got two operations, and the multiplication is distributed over the addition. Multiplication is of scalars and addition of scalars. And if we multiply scalars together, we get this kind of associativity. A times bx is the same as AB times x. We're taking A and B in here to be real numbers. So, I mean, there's the obvious properties of real numbers. Yeah, we've got commutativity of scalar multiplication. I could write this as B times A, for example. But we're not here to talk about that. You know what the real numbers are, I hope. They're a complete ordered field. The field properties give all the algebraic properties of the real numbers. And if we take any vector and multiply it by the scalar 1, the real number 1, you get the vector x back out. Preservation of scale, the book I use for sophomore linear algebra calls this. You might think of it as some kind of multiplicative identity scalar or something. Okay, we've taken the scalars to be real numbers. You need not do that. Vector spaces can be defined over any field, not just the field of real numbers. I might come at you with, well, how many fields do you know? The real numbers are fields, so we're good on that. How about the field of complex numbers? That's an excellent field. And dealing with vectors and matrices with complex entries, productive thing to do. And you go looking for, as you know from sophomore linear algebra, you go looking for eigenvalues of matrices. Even if everything you started with is real, those eigenvalues could be complex numbers, and that the eigenvectors could require complex entries. Maybe you glossed over that in sophomore level linear algebra. You take a second linear algebra class and it becomes important. It becomes important, these complex eigenvalues, in solving systems of linear differential equations. You might see that in an applied math class, introductory applied math class, second differential equations class maybe. But we could certainly do this over fields. In the Introduction to Modern Algebra 2 class, there's a section, there's a link here, section on vector spaces, and vector spaces are defined over fields. Probably the most useful field is, well, I say it's the complex numbers for reasons just elaborated on when we go looking for eigenvalues, for example. Other fields, yeah, there's study of finite fields out there. You'd explore finite fields in an abstract algebra, modern algebra class as well. The field of order 2, z sub 2, integers mod 2 with addition and multiplication, is useful in coding theory, for example. So there's certainly applications involving other fields than the real numbers. We're taking our lead from the book. The book is out of a Springer-Verlag series of books on statistics. So lots of real numbers that they're interested in. All right, so some of the definitions we have are very specific, excuse me, to the fact that we're dealing with vectors of real numbers. Two vectors in Rn. Now we actually write the vectors out. I'm going to try to use the square bracket notation to distinguish them from points in Rn. There's a difference in vectors in Rn and points in Rn. Vectors you can add together. You can't add points together. Vectors have magnitude and direction. They got magnitude. You know what the magnitude is. It's given by the norm of the vectors, and you know what that is in Rn. Direction's a little more vague as to what you mean exactly by direction. I'm happy to say that vectors in Rn have magnitude and direction. The magnitude we got no problem with. The direction's a little less clear. It's related to the existence of bases. You want to think of the basis vectors as representing directions in a sense. There's kind of n different directions in Rn. Well, there's an infinite number of directions in an informal sense, but a basis consists of n vectors, especially if I go to my favorite kind of basis, to an orthonormal basis. And then I could put a cleaner meaning on what I mean by direction. But in 3 dimensions, there's left, right, up, down, and forward, back. Any other, and that's 3, right? It's left and negative left, if you like, up and negative up. But those 3 fundamental directions can be used to determine any direction. Up and to the right, for example, is a combination of those. But even that's informal, and the idea of direction is informal. If we wanted to make it a little bit cleaner, we'd couch it in the language somehow or other of bases, probably orthonormal bases. But vectors in Rn, magnitude and direction. Points don't have magnitude, they ain't got direction either. Vectors don't have location. That's not the way you treat them when you deal with vector quantities in physics. Like location vectors, velocity vectors, force vectors, big time force vectors, don't have locations. Points are nothing but location. So there's a difference in vectors in Rn and points in Rn. We say that 2 vectors in Rn, x with components, x1 through x sub n, and y with components, y1 through y sub n, say they're equal if their corresponding components are equal. Just a quick side comment. The point, parentheses, x1, x2 through x sub n, close parentheses, the point doesn't have coordinates, it has components, just to get used to the lingo. The 0 vector in Rn is the vector of all zeros, n components, each of which is 0. You've maybe encountered that denoted with just a 0 in the past. That's a notation we used above. This book will sometimes use the symbol 0 sub n. It's the 0 vector with n components, which is kind of cool. That is a good notation there. Here's something that's probably new to you. The 1 vector in Rn, also called a summing vector, it yields sums when we do dot products, denoted by a 1 sub n, or simply a 1, and I don't like that, is the vector from Rn with all components of 1. Yeah, we'll generate sums. We'll do so really when we take dot products. So 0 vector you're used to, the 1 vector, I suspect that's new to you. It's fairly new to me, actually. Another definition, the things you do with vectors in Rn. So take vectors x and y with the usual type of subscripted components. Let A be a scalar, define the vector sum, x plus y to be the vector from Rn, with first component x1 plus y1, second component x2 plus y2, and so forth. You add vectors component-wise. Scalar multiple of vector x, take that scalar and you put it on each of those components. Is this distribution? Remember how I said distribution requires 2 operations? You ain't got but 1 operation. It's right there where the cursor is. It's the operation of scalar multiplication. This ain't distribution. There's nothing to distribute over. You might say we're distributing that A onto the components of this vector, but that's not a distribution property. And I wish you wouldn't call it distributing. Don't think distribution. That's a word in math that's used in a formal setting when you got 2 operations. When you got but 1 operation, scalar multiplication, and this is how it's this is how it's defined. So it couldn't be a distribution property, it's a definition. All right, so we add vectors component-wise, and we deal with scalar multiplication in this sense. So we've put at this stage, we've put an algebraic structure on vectors in Rn. No surprises. Some properties of that algebraic structure on vectors in Rn is the following 8 things say. We'll go through and prove the first one. Let x, y, and z be vectors in Rn. Let a and b be scalars. Then we claim the following. X plus y plus z equals x plus y plus z. Didn't we just do this? That's the first property we had above. Yeah, what we had above was the definition of a real vector space. What do these vectors look like in this vector space? No clue. Maybe they're n tuples of real numbers. Maybe there's something else. Maybe there's sines and cosines and linear combinations of those. Maybe they're exponential functions. Nobody knows in a vector space what the vectors look like. I know what the scalars are because they told us they're real numbers. The vectors, I don't know that these are n tuples of real numbers. What we're doing is showing in theorem 2.1 that the algebraic structure we've defined on Rn satisfies these 8 things. So we're dealing with a vector space. So we're showing that Rn with the algebraic structure we've given it is a vector space. So that's why these things look so similar. So we're establishing that on Rn, with that definition, we get a vector space with these properties. Okay, associativity, commutativity, identity, the 8 things we just listed are satisfied by vectors in Rn where we have a definition of vector addition and scalar multiplication is given. Let's go through, let's get things started slow, a proof of the first thing there. Okay, if I can find it, there it is. Okay, to the Beamer supplements. Let's go through a proof. I would do the same thing in sophomore linear algebra. So we're starting slow. Let x, y, and z be vectors in Rn. We claim associativity. All right. We got our brand new definition of vector addition. So, gee, is there some place where you know an associativity of vector addition? Well, there is in R. Real numbers form a field, associativity of addition, and a bunch of stuff. Okay, so well, let's go to that setting. Let's have vector x, vector y, vector z have the obvious components, subscripted x's, subscripted y's, subscripted z's, respectively. And let's get to the components. The components are real numbers, and I know we've got associativity of real numbers. So let's take x plus y plus z. In terms of the notation we just introduced, that'd be vector x plus vector y, added together first, plus vector z. How do you add vectors x and y together? Component-wise, so do that. We've already added those together first. Now add the z's in this vector sum. Definition of vector addition here, definition of vector addition here, but we added the x's and y's together first. So they get little parentheses around them. That was the first addition to do. Okay, now we've got real number x1 plus y1 added together first, and then real number z sub 1 added to that. Oh, but these are just 3 real numbers. I can use associativity of real numbers and move those parentheses from the x and the y to the y and the z throughout on all of those components. So the heavy lifting's done right here. You know the reals are associative, so we've used that property of the real numbers. We took the question of associativity in vectors, turned it into a question concerning associativity of real numbers. Use the associativity there. Now we just gotta unwind it. Common mathematical technique to take a question in one setting, vectors, turn it into a question in a different setting, the components of those vectors, that is, real numbers. Use your knowledge there and then take it and translate it back into the original setting, back into vectors. Okay, so we got the parentheses moved. Now we just need to unwind that and turn it into vectors. Okay, so here's where we left off. What we've got then is one real number plus another real number, first real number plus a second real number throughout. We can write that as a vector sum, the very definition of vector addition. All right. And within this, we have another vector sum. We've got vector y plus vector z from this, but that addition's being done together, and then the x's are being added on by the associativity that we had upstairs. And indeed, we have vector x plus the sums of vectors y and z. So we can move the parentheses over. How's that? Using properties of real numbers and going to the components of those vectors in Rn. How you prove this other stuff? How you prove commutativity? Same thing. write x and y in terms of components, write x plus y in terms of those component representations, add the vectors together, you'll get x1 plus y1 and so forth. Well, you can swap the order on those because the real numbers are commutative, and then unwind it. So the proof of, actually the proof of all of these is done in terms of components. And you've got distribution and all this stuff and identities in the real numbers. So we can use that to establish a corresponding property in Rn. So, hey, vectors in Rn satisfy all of these properties. That means that the space Rn is a vector space. Based on properties of the reals. Okay, so I'm going to refer back very, very often to this superb book by Fraley and Beauregard, dated. There's a lot of linear algebra books out there. Some of them are better than others. This is the best one I know. Catch me sometime. I'll tell you about some I don't like so much. But I've been using this book for the last 25 years. I actually used the second edition before that. I've used other books. This is the one to go to, especially with an eye towards more advanced classes, more math classes, and more matrix theory classes. It's a superb book. And I will refer to it often, and I'm borrowing results from it. These previous definition and that theorem 2.1.1, I got the proof at least directly out of the Fraley and Beauregard book, standard stuff. All right. Going to take our idea of adding vectors together and multiplying by scalars and define linear combinations. No news here. Take vectors v1 through v sub k, vectors from Rn. All our vectors are going to come from Rn. All our matrices, think all our matrices will have real entries. So almost exclusively considering real things. And we get in the eigenvectors and eigenvalues. We'll maybe have to talk in passing at least about complex numbers. But take vectors from Rn, take scalars from the reals. Linear combination resulting from those vectors and scalars is first scalar times first vector plus second scalar times second vector, and so forth. You know what a linear combination is. So what do you do to vectors? Yeah, you take linear combinations of them. That's why that class, that sophomore level class, is called linear algebra. The linear is this stuff. You might expect to see a bunch of lines in linear algebra. Yeah, not so much. Linear from linear algebra means this kind of behavior. Also, maybe the kind of behavior of linear transformations, which you encounter a lot in your graduate career. The concept of a linear function or linear operators. The set of vectors in Rn, as given here, are said to be linearly independent. These are definitions. If the only time we get a solution to the equation a1 v1 plus a2 v2 blah 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 plus a sub k v sub k equals 0, that'd be the zero vector, I can tell from context, is when each of those scalars equals 0. That's the zero scalar, I can tell from the context. The a's are scalars, the v's are vectors. So linearly independent means the only time a linear combination set equal to 0 is when all the scalars are 0. That's a linearly independent set of vectors. A set of vectors is linearly dependent if it's not linearly independent. All right. Let's unwind that last little statement there. So the logic, and this is standard stuff, what you saw in sophomore linear algebra. Standard definition for linearly dependent and linearly independent. As you know, we're really kind of more interested in linearly independent because we're going to go for bases for vector spaces. A common thing to do in linear algebra, common thing to do in applications as well, is to look for bases. Nice bases at that. So if I want to take this idea of linearly, it's linearly independent we're interested in. I highlighted the wrong one. If I want to call attention to these two things, linearly independent, this equation implies all those coefficients are 0. Excellent. Wouldn't be surprised if we didn't somehow relate this to a homogeneous system of equations and use matrix methods to establish that all of those coefficients must be zero. Being linearly dependent means this doesn't occur. So that's the thing I want to unwind and give a more direct statement. How would this not occur? That is, this equation implies all the coefficients are zero. This equation implies not all of the coefficients are zero. That is, some of them are non-zero. So a set of vectors v1 through v sub k is linearly dependent more directly if, for some scalars, a1 through a sub k, not all of them zero, yields a linear combination of those vectors equals zero. So some of these coefficients, at least one of these coefficients, is non-zero. Well, if that's the case, then we could take that vector, move it to the other side, and write that vector as a linear combination of the others. It reflects, I always explain it like this in linear algebra, dependent set reflects some redundance. One vector is redundant with the other. Of course, the right way to say that is one of the vectors is a linear combination of the others. Which one? The one that has a non-zero coefficient in this equation. If it's the second one, take that to the other side of the equation. We get a negative a sub 2, v sub 2 on this side. Divide both sides by that negative a sub 2, and you've got v sub 2 as a linear combination of the rest of them. Which ones? Well, I don't know, the ones that have non-zero coefficients. But think of linear dependence as redundance in terms of spans. More of that to come. Exercise 2.1 has you establish the following. The maximum number of vectors in Rn that forms a linearly independent set is n. So there's at most, at most, a set of vectors is linearly independent if it contains at most n vectors, maximum number of vectors. I could have lots of linearly independent sets, but I can't have any bigger than the size n when we take the vectors from Rn. You know where we're going with this. We're going for, and we haven't gotten there yet, he's worth pointing out, we're stating that Rn is a vector space, we got that, of dimension n. So we're going for talking about dimensions, which means we need to talk about bases. And you know we're headed in that direction when we introduce linear dependence and independence. Okay, the following, I do this a little different, but I'm following the book. Says, and so this is giving us, from this book, their approach at defining a vector space. A set of n vectors, via subset of Rn, vectors within components, is a vector space if it's closed under linear combinations. That is, if x and y are in this set of vectors, then for any scalars a and b, the linear combination ax plus by is in V. Okay. Now, they're not defining in this book vector space as generally as I did, actually as general as Fraley and Beauregard do in linear algebra. They're constraining everything to happen in Rn. So when they say vector space, they mean a vector space that consists of vectors from Rn. We've shown enough theory to establish that, yeah, Rn actually is a vector space itself. Of course, it's closed under linear combinations. It's all vectors in Rn. This definition jives a bit more maybe with how you dealt with subspaces of Rn. What does it mean for V to be a subspace of Rn? It's a set of vectors that's closed under linear combinations. So that's how you likely encounter this in sophomore linear algebra. We're studying for comprehensive exams. That's definitely what we're doing here. What they're really defining is subspaces of Rn when they say vector space. But the only kind of vectors this book considers, at least in the first 3 or 4 chapters, is vectors from Rn. So when they say vector space, in this book, they're really going at a subspace of Rn. And that's consistent with your sophomore level experience. Little bit unfortunate because there's some groovy vector spaces out there other than vector spaces related to Rn. And they're useful. You'll see them in applied math and differential equations. They pop up all the time. Infinite dimensional vector spaces will pop up all the time in those applications as well. Not for us. Everything in here, as is standard in a theory of matrices class, everything in here will be finite dimensional. You want to go to the infinite dimensions, that's more the realm of analysis and functional analysis. I've added this exercise to give us a more rigorous approach to the definition of dimension. For vector space V, as we've defined above, subspace of Rn, if W1 and W2 are finite subsets of V, which are linearly independent and of maximal size, then W1 and W2 are the same size, same cardinality. That is, W1 in cardinality equals W2 in cardinality. So we've got linearly independent subsets of maximal size. They're subsets of a given vector space V. They have to be the same cardinality. We're going at saying, so when we define basis, we're going to see from this that all bases are the same size. That same size is what we'll call the dimension of the vector space V. But the statement here, W1, they're subsets, they're linearly independent, and they're as big as they can be. So maximal size linearly independent subsets of vector space V are the same cardinality. We'll define that as the dimension, maybe indirectly, but that'll be the implication. Next definition is the maximum number of linearly independent n-vectors in a vector space V is called the dimension of that vector space, dimension of V. How do you know? Different maximal size linearly independent sets are even the same size? Well, by that comment that we just made. Dig through your sophomore linear algebra book. You develop it the same way. You show all linearly independent spanning sets are the same size, probably in linear algebra. Similarly, that's what we're doing here. So that justifies calling it the dimension of a vector space, since all these maximum linearly independent sets are the same size. That's the dimension of the space. The order of the space, this is probably a new word to you. It's the number of components. It's n. I mean, we're only considering n vectors, so n is called the order of the vector space. Rn is both order n and dimension n, but I could have, say, a three-dimensional subspace of R4. That 3 dimensions would give us the dimension of the subspace, but if it's a subspace of R4, the vectors all have 4 components. So it could be a 3-dimensional subspace of vectors with 4 components, say. And then we'd say the order of that subspace would be 4, yet the dimension is 3. Okay, I'm going to get a little more vocabulary, pile of vocabulary in this first section. 2 vector spaces, V1 and V2, both of order n. So they're both subspaces of Rn. Not to use our lingo, but maybe some lingo familiar to you from the past. They're said to be essentially disjoint if their intersection is the 0 vector. That must be the 0 vector in Rn. Every vector space contains the 0 vector. It's part of the definition, no matter how you slice it. There's 0 vectors in all vector spaces. If they are both vector spaces, which are subspaces of Rn, then it's the same 0 vector. 2 vector spaces, subspaces of Rn, couldn't be totally disjoint because of 0 vectors in both of them, but they could be essentially disjoint. So the only thing in both of those vector spaces is the 0 vector. One way to think about it, harking back to your linear algebra experience, is if those 2 vector spaces are maybe orthogonal to each other, Maybe they're orthogonal complements in Rn. If that's the case, the only thing they would share would be the 0 vector. And with orthogonal complements, it gives you a geometric picture. Think about maybe V1, let's do this in R3. Think about maybe we're in R3, V1 is all vectors that in standard position lie in the XY plane. V2 could be all vectors that point directly up or directly down. In standard position, they lie along the z-axis. So we got the floor down here, and we've got the z-axis here. The only place they intersect is at the 0 vector. So I like geometry when it's there. As long as we're talking Rn and nothing too exotic, we probably get geometry out of these. The ith unit vector in Rn, denoted E sub I, we'd normally put a little hat over this. In linear algebra, we do it that way. Is a vector that has a 1 in the ith position and zeros in all of the other positions. So E sub I is 0, 0, 0, 0. When we get to the ith position, there's a 1, 0, 0, 0, 0. You're probably familiar to describing this as the ith standard basis vector of Rn. So it's a vector of all zeros with a 1 in the ith position. For a vector with components x1 through x sub n, the sign is defined as a vector, sine of x, which is, first component is the sine of x1, which is plus or minus 1 or possibly 0. Sine of x2 up through sine of x sub n. This sign of a real number, it's 1 if the number is positive, it's -1 if the number is negative, and it's 0 if the vector is 0. So this allows you, in some sense, to encode the sign of the components of this vector in a vector, getting out 0 for 0 components, 1 for positive components, and -1 for negative components. I don't know that we'll use this too much, and it pops up in passing in the things we do. More in line probably with taking vectors that contain some type of data, and we're interested in positive or negative or 0. And ordering, this will come up along the way, but not a great deal. It's stuff, if it's a graduate student, I know you've seen this before. And ordering, denoted with this little symbol here, it's like a curvy less than or equal to. An ordering on a set is a relation that's reflexive, transitive, and anti-symmetric. By anti-symmetric, I mean let me get this straight. If we have both A is less than B and B is less than A, and we may not have that for all A and B in the set, so I pause to get this stuff straight, then we must have A equals B. So when you reverse the inequality, the only time both of those hold is when A and B are the same. A total ordering on a set A is an ordering such that for any A and B on which this ordering is defined, we get either A is, let me read it, less than or equal to B, or B is less than or equal to A. Possibly you get both of them. But sometimes for orderings on sets, not total orderings, you can't compare A and B. We'll have an example down below. An ordering on set A, which is not a total ordering, it's called a partial ordering. A result from set theory says every set can be partially ordered. We don't want to dig too deep into set theory. I don't like this stuff, but orderings will pop up in passing. We'll use them most commonly, and maybe you've seen them in algebra classes. They pop up in this setting where we talk about ordering sets using set inequality. Set inclusion. For example, if we take less than or subset or equal to, we can define a partial ordering on here's set A. It has as its elements the set consisting of A, the set consisting of B, and the set consisting of AB. then we could say, hey, A is set consisting of A is less than or equal to the set consisting of A and B. B is less than or equal to the set consisting of A and B. We can't compare A and B under this partial ordering, though. That's why it's a partial ordering. We can't say A is a subset of B or B is a subset of A, subset or equal to. Neither of those hold. So I would say this set, this element of set A, and this set, this element of set A, they're not comparable. We don't have this, either this or this. We don't have a total ordering. This is a partial ordering because these aren't comparable. Also, I'd make my set A bigger. If we do have one thing is a subset of the other and the other is a subset of the one, then of course the sets have to be equal. So we get this anti-symmetry thing satisfied. It's common to use set inclusion to introduce partial orderings, and it becomes partial because of the non-comparability. I can have subsets that neither one is a superset of the other. They might overlap. Here they don't. They might be disjoint, but I might not have one as a subset of the other. So they're not comparable under such an ordering. We're going to define, it's the first time I've seen this, I must admit, define a partial ordering on Rn, the vectors in Rn as follows. We'll say that x is greater than y, vector x is greater than vector y, denoted vector x is greater than vector y, if x sub I is greater than y sub I for I equals 1 through n. That is, if every component of the x vector is greater than the y vector, we'll write this inequality. If every component of the x vector is greater than or equal to every component of the y vector, we'll write greater than or equal to. So this allows us to put partial ordering on the vectors in Rn. Remember, this book comes out of a statistics sequence, so there's probably some sort of comparison of data that they have in mind when they go to this, and that's probably why I haven't seen it in my travels. My travels have been mostly analysis things. I've dealt certainly with matrices, and matrices tie in with linear operators. I've dealt a bit with linear operators, maybe in infinite dimensions, where, hey, you're dealing with matrices. Hey, in infinite dimensions, you're dealing with infinite matrices, just like you would for linear transformations on Rn. But applying this with data, as a statistician would, is fairly new to me. So this is a totally new definition to me. Let's do a little bit more. We'll take a little break from the video. A subset of a vector space V that is itself a vector space, it's called a subspace. So here's a subspace of a vector space. By the way, could observe now formally with the definitions these folks have introduced that now that means every time we've said vector space V, we're dealing with a subspace of Rn because we're only considering vectors that are subspaces of Rn. The vectors are themselves n tuples of real numbers in here. So this definition lets us clear that up a little bit. What is a vector space? One more time. In Gentle's book let's run back and check. It wasn't those 8 axioms. In the book, a vector space is a collection of n vectors that's, here you go, closed under linear combinations. Collection of n vectors, it's closed under linear combinations. That's a vector space. So if we want to show something's a vector space, all we got to do is show closure under linear combinations. Down here, we're claiming, theorem 2.1.2, if V1 and V2 are vector spaces of n vectors, then V1 intersect V2 is a vector space. All right, so what we need to show is intersections of vector spaces are vector spaces. Vector spaces are collections of n vectors that are closed under linear combinations. So by the way, saying V1 and V2 are vector spaces of n vectors is saying both of these closed under linear combinations. We want to show the intersection is closed under linear combinations. Well, we want to show the intersection is a vector space. That is, we want to show the intersection is closed under linear combinations. And that should be a total piece of cake. So let's go through the proof of this. I appreciate your patience. It'll pick up. Where we want to show an intersection of two vector spaces is a vector space. All right. We need, by our definition of vector space, we need to deal with closure under linear combinations, which is not different from how you dealt with showing something's a subspace in linear algebra. You showed it was closed under linear combinations, a subspace of a given space. Okay, so take two vectors, x and y, in the intersection, and take a and b to be scalars. All right. V1's a vector space, so we've got closure under linear combinations. That is, if we take ax plus by, that will be in V1 because it's a vector space. Ax plus by will be in V2 similarly. So we took an arbitrary pair of vectors in the intersection. We've shown that a linear combination is in both V1 and V2, so it's in the intersection. Those were arbitrary vectors, arbitrary elements of V1 intersect V2, arbitrary scalars. So every linear combination of two vectors, and by induction, more vectors if you like, of vectors in V1 intersect V2, the linear combination is in the intersection of V1, V2. We've got closure under linear combinations. So indeed, V1 intersect V2 is a vector space that is closed under linear combinations. Union of two vector spaces of n vectors need not be a vector space. You're asked, I guess, to give an example in exercise 2.2. Piece of cake. Those orthogonal complements we were talking about earlier would work fine to give an example of two vector spaces, the union of which is not in itself a vector space. You lose, not being a vector space, you'd lose closure in the union under addition if I took orthogonal complements. I leave it to you to sort out the details. But like orthogonal complements, there's geometry there. The text refers to a set of vectors of the same order as a space of vectors. Yeah, I don't like that. That reminds me too much of vector space. And all I got is a set of vectors. I'm going to call a set of vectors a set of vectors, set of n vectors for us, and avoid this space verbiage. That's not a good term. Reminds me too much of vector space, which implies closure under linear combinations, and we need not have that just in a set of vectors. I mean, that's what you're showing in that exercise. All right, here's something pretty straightforward, something maybe you didn't deal with in sophomore level linear algebra, is a sum of two vector spaces. I know the union need not be a vector space. That's what you're asked to show in that example. Here we're defining the sum. Take V1 and V2 to be, so we're defining it for sets of vectors. My favorite sets of vectors are vector spaces. But we're taking two sets of vectors and defining the sum of those sets of vectors, V1 plus V2, to be the collection of all lowercase v1 plus lowercase v2, where v1 is a vector from set of vectors v sub 1, and v sub 2 is a vector from set of vectors v sub 2. So it now makes sense with this definition to add together sets of n vectors. Got to have the same number of components for the addition to be defined. Hey, all this is going on inside Rn, given our setting. And theorem 2.1.3 says if v1 and v2 are themselves vector spaces of n vectors, then v1 plus v2, in this sense, is a vector space. So a sum of vector spaces is a vector space. Let's check that out. It's just checking for closure under linear combinations. Okay, let's show v1, v2 vector spaces. v1 plus v2 is a vector space. Yeah, in the setting is everything is a vector within components, in real components. Okay. We just need to deal with linear combinations by the definition of vector space is fed to us by the textbook. So we need to take two vectors, x and y, in v1 plus v2, arbitrary scalars a and b. We need to show the linear combination ax plus by is indeed in v1 plus v2. We need to show closure under linear combinations of v1 plus v2. Sufficient to do for two vectors. Induction will take care of linear combinations of multiple vectors. Okay. Well, hey, if x is in v1 plus v2, what was this again? This was a collection of all vectors of the form element of v1 plus element of v2. Vector in v1 plus vector in v2. So we can take this x vector and write it, say, as an x sub 1 plus x sub 2, where x sub 1 is a vector in v1 and x sub 2 is a vector in v2. That's what it means to be in v1 plus v2. And we can do the same thing for vector y. So we can take vector x and vector y, write them as these types of sums. After all, that's what v1 plus v2 was, is a set of vectors. Okay. So let's see, v1 and v2 were given to be vector spaces. They're closed under addition. In particular, closed under linear combinations because they're vector spaces. If we take ax1 plus by1, since x1 and y1 are in v1, then the linear combination is in v1. Closure under, should be closure under linear combinations. x2 and y2 are in v sub 2, so the linear combination ax2 plus by2 are also in v sub 2. Okay. So if we look at ax plus by, remember we took arbitrary vectors, x and y, in the alleged vector space, arbitrary scalars. Here's a linear combination. If we can show that's in v1 plus v2, and it looks like we're about to, then we're done. Because that shows closure under linear combinations. All right, what was up with ax? X we had written is x1 plus x2, so we'll substitute there. Y we had written is y1 plus y2, where the subscripts indicate where these pieces of those vectors come from. We can rearrange that. Let's get the ax1 plus bx1 together. Let's get the ax2 by2 together. Get the subscripted 1s together, the subscripted 2s together. We just said this thing is in v1 and that thing is in v2. We're adding these together, so we're getting an element of v1 plus v2. So it's a matter of writing ax plus b in the appropriate form to show that it's explicitly in v1 plus v2. And these were arbitrary vectors, arbitrary scalars. We've got closure under linear combinations. Closure under linear combinations, it's a vector space, because in here, that's what a vector space is. Collection of n vectors that's closed under linear combinations. All right, so that takes care of sums. Next thing deals with a related topic. Let's take a little break and we'll come back and work more. It'll take us a while to get through this first section. There's a bunch of stuff here. Most of it not complicated. A lot of it things you've seen before. Some of it some kind of weird new definitions, like this one vector, for example. Let's take a little break. We'll be back at it soon. Bye-bye.